Introduction. Born of stars, a cosmic reflection. Long before the Earth was formed, before the moon circled our skies, before life breathed for the first time in shallow seas or whispered through forests of green, the universe was forging the very ingredients that would one day become us. In the beginning, there was only hydrogen and helium, two simple gases drifting through space after the birth of the cosmos. There were no planets, no oceans, no minds to wonder, just darkness, gravity, and the whisper of time. But then, something extraordinary happened. Clouds of these primitive elements collapsed under their own weight, igniting in brilliant bursts of fusion. The first stars were born, and with them, the story of everything that would ever matter. Inside those stars, under crushing pressure and unimaginable heat, the elements of life began to take shape. Carbon, oxygen, iron, calcium, gold. Every atom heavier than helium was forged in these cosmic furnaces. And when these stars reached the end of their lives, whether quietly fading or exploding in dramatic supernovae, they scattered their contents across space like seeds in the wind. That stardust, tiny particles of matter once trapped in the hearts of ancient stars, drifted for billions of years, eventually forming new stars, new planets, and one day, life itself. Our sun, our planet, our bodies, even the thoughts that carry you gently towards sleep tonight, are made of that same ancient material. Stardust is not just poetic metaphor, it is literal truth. You are, in the most profound sense, a child of stars. This is the story of how the universe evolved from the death of celestial giants to the birth of life as we know it. It is the journey of atoms and dust, of chaos and creation, destruction and rebirth. It is a gentle path that winds through billions of years, leading us to one quiet, humbling realization. The universe is not just out there, it is within us. In this audiobook, we will explore how stars live and die, how their remains travel across the galaxy, and how those ancient particles eventually found their way into rivers, mountains, flowers, animals, and us. We will follow the life cycle of matter, from the heart of exploding suns to the soft tissues of living beings. And as we drift deeper into these chapters, remember that every breath you take, every heartbeat, every blink of thought is powered by atoms born in long-dead stars. You are a symphony of ancient light and matter still echoing through the universe. So now, close your eyes, quiet your thoughts, and let us begin.
Chapter 1. The Universe's Dusty Secret. When we imagine the universe, we often picture grand things, brilliant stars, vast galaxies, mysterious black holes, and swirling nebulae painted across the darkness. We think of light and motion, of gravity and silence. Rarely do we consider dust. Yet hidden in the quiet corners of space, in the invisible veil between the stars, dust drifts endlessly. Tiny grains, smaller than a grain of sand, roam the cosmos on journeys older than the Earth itself. These particles, often overlooked, are the storytellers of the universe. Within each speck lies a memory, a record of ancient processes that shaped everything we know. Cosmic dust is not like the dust we find in our homes. It is born in violent and extraordinary places, in the outer atmospheres of dying stars, in the explosive ends of supernovae, and in the winds of red giants. These grains are composed of silicates, carbon, metals, and ice. Each grain a relic, each one a traveler. After a star dies, its remaining material is flung into the surrounding space, spreading the heavy elements it once forged. In the chill of interstellar space, atoms collide and combine, forming solid particles, dust. Billions of them, carried by stellar winds and shock waves, begin their endless voyage through the galaxy. Some grains may wander for eons, never colliding with anything. Others find their way into new clouds of gas and dust, nurseries for future stars and planets. Astronomers used to think dust was a nuisance. It obscured their view, dimming the light of distant stars and galaxies. But with time, we realized that dust was not blocking our view of the universe, it was revealing it. With the right instruments, scientists began to see the warm glow of dust in infrared light. These observations opened a new window, allowing us to peer into places where stars are born, where planets take shape, and where the raw ingredients of life begin to assemble. Dust plays a quiet but crucial role in the story of creation. It helps clouds of gas collapse into stars. It shields fragile molecules from harsh radiation. It carries water and organic compounds across space. It acts as the canvas on which the chemistry of life is painted. Without cosmic dust, there would be no Earth, no oceans, no air, no plants, no animals, no people. We owe our existence to the grains that drifted through space long before our sun lit the sky. These tiny fragments of former stars seeded the universe with possibility. Over billions of years, gravity gathered them together, sculpting planets, cradling atmospheres, and igniting sparks of biology. Even now, the Earth continues to receive a gentle rain of stardust. Each day, tons of micrometeorites fall from space. They are remnants of the same process that gave rise to the planets. If you've ever seen a shooting star streak across the night sky, you've witnessed cosmic dust burning in our atmosphere, a fleeting trace of something ancient returning home. But this dust is not uniform. Some grains come from massive stars that ended their lives in supernovae, their cores collapsing and exploding outward in a final act of brilliance. Others formed in the quiet winds of long-lived stars, slowly shedding their outer layers into space. Some have been altered by cosmic rays, others shaped by collisions in asteroid belts or comets. Each one is unique, a fragment of a different chapter in the universe's story. Scientists have even collected and studied dust particles from space. Missions like NASA's Stardust brought samples of comet dust back to Earth, revealing complex organic molecules, chains of carbon that hint at the prebiotic chemistry that may have played a role in life's origin. These findings suggest that the seeds of life might be far more common than we once believed. Cosmic dust teaches us that the universe is not sterile or empty, but full of potential. It tells us that the elements required for life are not limited to Earth, but scattered throughout the cosmos, waiting to be gathered again. It reminds us that even the smallest particles can carry the weight of the universe's history. In many ways, dust is the memory of stars. It is the residue of cosmic creation, the ash of celestial fire. And though it drifts silently through the vacuum of space, it is never truly still. It is always becoming something more, part of a comet, part of a planet, part of a living cell. As you breathe in the calm of this moment, consider the grains that float between stars. Consider that some part of you was once part of them, that the iron in your blood,
the calcium in your bones, the carbon in your cells, all once formed in the heart of a dying star, scattered as dust, and eventually came to rest in you. This is the dusty secret of the universe, that even in death, stars give. They give form, they give substance, they give life. And their gift is written in the particles that drift through time, waiting to be reborn. Let us now follow that journey deeper and uncover how stardust continues to shape the cosmos and us.
Chapter 2: Stars, the Original Forges. At first glance, stars appear as simple points of light scattered across the night sky, distant, untouchable, eternal. But behind their calm glow lies a truth that is anything but simple. Stars are the original forges of the universe, enormous, blazing factories where matter is transformed, where the lightest elements become the heavy atoms that will one day shape worlds and living beings. To understand how stars forge the universe, we must return to a time when the cosmos was young. In the early universe, only hydrogen and helium existed in any significant amount. These elements, born during the Big Bang, floated freely through space in vast cold clouds. But gravity is persistent. Over millions of years, it tugged at these clouds, drawing the gas into dense knots. As more and more matter gathered, the pressure rose. The center of these clouds grew hot enough to ignite something extraordinary: nuclear fusion. This was the birth of the first stars. Inside a star's core, atoms are forced together under immense pressure. When hydrogen atoms fuse, they form helium, and in that process, a tiny amount of mass is lost and converted into energy. That energy is what powers a star. It is what makes it shine. It is what pushes against the force of gravity and keeps the star from collapsing. For billions of years, this delicate balance continues. But hydrogen, though abundant, is not infinite. When a star exhausts its hydrogen fuel, it begins to change. In smaller stars like our Sun, the core contracts while the outer layers expand, forming a red giant. The star then begins to fuse helium into heavier elements like carbon and oxygen. Eventually, the star sheds its outer layers into space, leaving behind a white dwarf, a dense, hot core that slowly cools over time. In massive stars, the story is even more dramatic. These giants can fuse elements far beyond helium, forming neon, magnesium, silicon, and eventually iron. But fusion cannot continue forever. When iron forms in the core, the process stops. Iron cannot be fused into heavier elements without consuming more energy than it produces. With nothing left to sustain it, the core collapses. What follows is one of the most powerful events in the universe: a supernova. In a fraction of a second, the star implodes and then explodes, scattering its layers into space. In the process, elements heavier than iron, gold, uranium, lead, are created in a final furious burst of energy. These explosions are so intense that they briefly outshine entire galaxies. And then, from that destruction, something remarkable happens. The debris from the supernova, enriched with all the elements it has created, expands into space. This material will one day become part of new stars, new planets, and new forms of life. The cycle begins again. This process, fusion within stars, and the explosive events at their end, is the primary way that heavy elements are made in the universe. Without it, there would be no carbon for the cells in your body, no oxygen to breathe, no silicon for rocks, no calcium for bones. All of it began in the hearts of stars.
It is an elegant irony. Stars, which seem so far and beyond us, are in fact deeply connected to everything we are. Their births gave the universe light. Their lives gave it warmth. Their deaths gave it substance. In their glow, we see not just beauty, but history. Even now, stars continue their ancient task. All across the universe, they burn steadily, fusing hydrogen into helium, helium into carbon, and so on. The same reactions that powered distant suns also powered the creation of our very atoms. You are quite literally built from the ashes of stars that lived and died billions of years ago. This stellar alchemy is not just a scientific process, it is a cosmic story of transformation. From the simplest elements came complexity. From the fire of fusion came the potential for life. The furnace of a star is not just a place of burning gas, it is a birthplace of everything we hold dear. The next time you look at the night sky, try to imagine what lies within each tiny point of light. Picture the chaos and brilliance within its core, the immense pressures, the boundless energy. And then consider this. The atoms that make up your body have seen that same brilliance. They were once part of something just as luminous, just as powerful. Stars are not just lights in the sky. They are the great architects of matter, the original alchemists of the cosmos. They are our ancestors in a way more profound than any myth or story could suggest. As we move forward, we'll explore how the dramatic ends of these stars, especially supernovae, play a vital role in scattering the seeds of life across the universe. Because in their death throes, stars do not vanish, they give.
Chapter 3: Supernovae and Stellar Alchemy. There is a quiet dignity to the life of a star. For billions of years, it shines with unwavering brilliance, maintaining a delicate balance between gravity's pull and fusion's push. But when that balance breaks, the end is anything but quiet. The death of a massive star is among the most violent and awe-inspiring events the universe has ever known. It is also one of its most creative. This dramatic finale is known as a supernova. To truly understand a supernova, we must first revisit the heart of a massive star. Throughout its life, the star burns through layers of fuel, first hydrogen, then helium, and onward to heavier and heavier elements, carbon, neon, oxygen, silicon. Each fusion reaction supports the star, keeping it alive. But with each new element forged, the energy balance becomes harder to maintain. Eventually, the star reaches a fatal threshold: iron. Iron is different from the other elements. It cannot be fused into heavier atoms without absorbing more energy than it releases. When iron accumulates in the star's core, fusion grinds to a halt. Gravity, long held at bay, now wins. In a flash, the core collapses. The collapse is catastrophic. The core implodes, compressing matter into an unimaginably dense state. In mere seconds, the outer layers rebound off the core and explode outward in a titanic shockwave. This is the moment of the supernova, a flash of light so bright it can outshine an entire galaxy for a brief time. But out of this chaos comes something extraordinary: the creation of elements heavier than iron. This is where stellar alchemy reaches its peak. In the intense temperatures and pressures of a supernova, atomic nuclei are smashed together with such force that new, heavier elements are born: gold, silver, uranium, platinum. Elements that never could have formed under normal stellar conditions are suddenly forged in the blink of an eye. These are the final precious gifts of a dying star. And then, just as quickly, the light fades. What remains may be a neutron star, a city-sized object of incredible density, or a black hole,
where gravity is so strong that not even light can escape. But surrounding it is a vast cloud of newly made elements, expelled into space, drifting, cooling, and mingling with the interstellar medium. These clouds, rich in stardust and heavy atoms, will one day seed new star systems. They are the ingredients for planets, oceans, mountains, and DNA. In a cosmic sense, every violent death of a star becomes the gentle beginning of something else. Astronomers have long been fascinated by these events. Some of the earliest recorded supernovae were observed by ancient Chinese and Arabic astronomers, who saw guest stars suddenly appear in the sky, shining for days or weeks before vanishing. Today, with powerful telescopes, we can study the remnants of supernovae, great expanding clouds of glowing gas, such as the Crab Nebula, a relic of a stellar explosion witnessed on Earth nearly 1,000 years ago. And we now know that our own solar system was likely born from the remains of such an event. The presence of certain elements in meteorites, elements that can only be formed in supernovae, suggests that long ago a star died near the cloud of gas and dust that would eventually become the Sun. Its explosion may have triggered the collapse of that cloud, setting into motion the chain of events that led to our existence. So in a very real way, we are the children of a supernova. The calcium in your bones, the iodine in your thyroid, the gold in your jewelry, all of it was formed in the final seconds of a star's life. These elements are not just byproducts of destruction, they are the outcome of transmutation, the ultimate alchemy of the cosmos. And the story doesn't end there. The matter expelled by a supernova doesn't simply drift aimlessly. Gravity begins its slow work once again. Over millions of years, the dust and gas begin to gather. The cycle repeats. New stars are born from the ashes of old. New planets form from ancient debris. And in rare, quiet corners of the galaxy, life may one day emerge again, built from the shattered heart of a long-dead sun. There is something deeply poetic about this cycle. Stars burn brightly, exhaust their fuel, and die in fury, but they do not die in vain. They leave behind the tools for creation. Their final breath is a promise that something new will rise from their fall. The next time you hold a piece of metal in your hand, or watch the golden light of sunset spill across the sky, remember that you are witnessing the afterglow of ancient stars. You are surrounded by their gifts. You are made of their final moments. This is the magic of supernovae, a violent death, a generous end, and the quiet beginning of everything that follows.
Chapter 4: Cosmic Winds and Stellar Ashes. The death of a star is not always marked by sudden explosion. Sometimes it happens slowly, like the fading of a fire whose embers still glow in the dark. In these quieter endings, the universe breathes out, gently exhaling the materials of life into the cold reaches of space. These exhalations are known as cosmic winds, and they carry with them the ashes of stars, dust and gas that will one day be reborn in new forms. Imagine a massive star near the end of its life. It has lived for millions of years, shining brightly, fusing lighter elements into heavier ones deep in its core. As it runs low on fuel, it begins to swell. The star becomes a red giant, its outer layers expanding thousands of times beyond its original size. The gravity at its surface weakens, and from this fragile outer shell, particles begin to drift away. These are stellar winds, flows of material pushed outward by the star's radiation and temperature.
Over time, the star loses a significant portion of its mass to these winds, sending carbon, oxygen, silicon, and other heavy elements into space. This process is not violent like a supernova, but it is no less important. In fact, for certain elements, this is the primary way they are distributed through the galaxy. The material ejected forms vast clouds around the star, shells of glowing gas and dust illuminated by the central core that remains. These are known as planetary nebulae, a name given long ago when their rounded shapes reminded early astronomers of distant planets. But these nebulae are not planets, they are the soft shrouds of dying stars. And at the center of these nebulae lies a white dwarf, a hot, dense remnant about the size of Earth, but with a mass close to that of the Sun. It no longer fuses elements. It no longer shines from within. It glows only with the residual heat of a long and luminous life. Over billions of years, it will slowly cool and dim, fading into the background of the cosmos. These stellar winds and ashes drift into space, merging with the interstellar medium, the vast, thin soup of gas and dust that fills the space between stars. Over time, these materials gather, mixing with other particles from other stars, forming the complex and rich clouds that will give birth to the next generation of suns and worlds. This cycle, birth, life, loss, and rebirth, is one of the most elegant rhythms in the universe. Stars are not isolated entities, they are part of a continuum, each one inheriting the matter of those that came before, and each one passing that matter onward. Even the smallest particles in the solar system, microscopic grains in a meteorite, or flecks of dust floating in the tail of a comet, contain within them the story of ancient stellar winds. We often think of wind as a force that moves leaves, carries scents, or whispers through trees. But in space, winds have no air. They are made of charged particles, protons, electrons, and atomic nuclei, streaming outward at incredible speeds. And just as Earth's winds shape our weather and landscapes, cosmic winds shape galaxies. In fact, some of the most powerful winds in the universe emerge from supermassive black holes at the centers of galaxies. As matter falls toward the black hole, it heats up and blasts outward in jets that can carry material across tens of thousands of light years. These galactic winds help regulate star formation, blowing away the gas that could form new stars and enriching vast regions of space with heavy elements. Even our own sun produces a wind, a gentle but constant stream of particles known as the solar wind. It shapes the tails of comets, creates auroras on Earth, and defines the boundary of our solar system. In this way, even living stars share their material with the void, echoing the processes of their dying counterparts. So when we speak of the ashes of stars, we are speaking of gifts of carbon that will form the backbone of living molecules, gifts of oxygen that will one day flow in alien atmospheres, gifts of iron and silicon that will shape the crusts of distant worlds. These ashes are not signs of loss, but of continuity. In every direction we look, space is filled with the quiet presence of what once was. The faint glow of nebulae, the trace elements in meteorites, or the distant shimmer of dust clouds, they are the legacy of stellar winds, the breath of stars suspended in time. And within your body, your bones, your blood, your breath, there are atoms that were once carried by these winds, blown across space, gathered by gravity, joined into cells. You are part of that great cycle. You are not just a witness to the universe's story. You are made of its memory. Let yourself imagine now the slow dance of dust in a nebula, drifting through silence, illuminated by the fading light of its parent star. No sound, no motion that we could feel, just a slow dispersal of matter, a gentle return. In this quiet process, the universe prepares itself for the next chapter, and we are here billions of years later to write part of that story.
Chapter 5. The Journey Through Interstellar Space. The space between stars may seem empty, silent, and still. A great dark nothing stretching endlessly in all directions. But that vastness is not a void. It is a sea of dust, gas, magnetic fields, and cosmic rays. And within it, the remains of stars, the particles forged in fire, drift through the galaxy in a slow, quiet migration. This is interstellar space, the medium through which stardust travels. After a star dies, whether in a quiet shedding of layers or in a violent supernova, the particles it releases begin their long journey. Freed from the pull of their parent star, they move outward, propelled by winds or explosions, and begin a slow drift through space. These particles, smaller than a speck of smoke, are carried on invisible currents. Some are solitary travelers. Others form clouds, nebulae, and filaments glowing faintly in the infrared. They do not move fast by human standards. A grain of stardust might travel just a few kilometers per second, far slower than the speed of light, and yet still fast enough to cross great distances in time. In the vastness of space, patience is not just a virtue, it is the nature of things. But this journey is not without challenge. The space between stars is not completely serene. It is filled with radiation from other stars, with cosmic rays that can alter the structure of atoms, and with shock waves from distant explosions. Dust grains are battered and weathered, sometimes even shattered. Others may be caught in magnetic fields or swept into larger clouds of gas. Some are lost forever, but many survive. These grains of dust, forged in the depths of stars, spend millions, sometimes billions of years traveling. Along the way, they may encounter strange places, the outer edges of star systems, cometary tails, or the gravitational pull of new stars forming. Some may become embedded in the cold bodies of asteroids or frozen into comets. Others may float through empty space until they are drawn into a new home. Some of these ancient particles have even reached us. Every day the Earth is visited by interstellar dust, microscopic grains that penetrate our solar system and fall through our atmosphere. Scientists have captured some of these particles using high-altitude aircraft or delicate collectors in space. Inside them, we find carbon, oxygen, iron, silicates, proof that even the smallest grains can carry the fingerprints of distant stars. One of the most extraordinary missions in recent history was NASA's Stardust spacecraft, which collected dust from the tail of Comet Wild 2 and returned it to Earth. Among its samples were particles older than the solar system itself,
grains formed around ancient stars long before our sun was born. These tiny fragments held within them clues to the galaxy's past and possibly to the chemistry of life itself. As these grains drift, they become part of something larger. In the cold reaches of space, dust and gas begin to gather, slowly, imperceptibly. Gravity begins to tug. Particles bump, stick, merge. Over millions of years, these clouds collapse into spinning disks. From these disks, stars are born, and around them, planets begin to form, tiny pebbles of dust becoming rocks, then worlds. Thus, the journey of a single dust grain can end in something as grand as a planet or something as delicate as a flower. Imagine for a moment a single particle of carbon forged in the core of a star. It explodes outward, travels for billions of years, drifts across light years of space. It joins a cloud, falls into a newborn solar system, becomes part of a comet. That comet collides with a planet. Rain falls, oceans form, life begins. That carbon atom becomes part of a cell, a leaf, a thought, and now it is part of you. This is the miracle of the interstellar journey, not just that matter moves across the galaxy, but that it transforms, that what was once part of a star can become part of a tree, a whale, a heartbeat. That even the smallest speck of dust can become meaningful when given enough time and the right conditions. We tend to think of travel in terms of purpose and destination, but for stardust, there is no map, only motion, only possibility. The journey is not linear, it is circular. Matter becomes energy, then matter again. Stars become dust, dust becomes stars, and through it all, the universe whispers its ancient rhythm, from fire to silence, from silence to form. So, as you lie back and listen, know that within your body are travelers, atoms that have journeyed across unimaginable distances and epochs. They have seen stars born and die. They have waited in the cold, in the dark, for a chance to be part of something again. And now they live as part of you. The next time you gaze at the night sky, try to imagine those silent travelers drifting between the stars, invisible, patient, timeless, the ashes of stars, still moving, still becoming.
Chapter 6: A Second Generation, The Birth of Enriched Stars. After the dramatic deaths of the first stars, those massive, short-lived pioneers, the universe was left with something it had never known before, a wealth of heavy elements scattered across the cosmic fabric. The hydrogen and helium that once dominated now floated beside newly born atoms, carbon, oxygen, nitrogen, iron. These enriched materials didn't vanish into the cold silence. Instead, they began to congregate, quietly, forming the building blocks for the next generation of stars. These second-generation stars, often referred to as population 2 stars, were different from their ancestors. They were not born from a pure primordial soup, but from clouds laced with stardust, the ashes of ancient celestial titans. Their existence marked a profound turning point in the history of the cosmos. The era of chemical enrichment had begun. In these new stars, the presence of heavier elements subtly changed their behavior. These atoms acted like tiny thermostats, regulating the cooling of gas clouds more efficiently. With better cooling came more efficient star formation.
Smaller, longer-lived stars began to emerge alongside their massive siblings. For the first time, the universe was not just creating stars that would quickly burn and die, but stars that could endure for billions of years. Some of these enriched stars still burn today. They're visible in the old globular clusters that surround our galaxy, shimmering like ancient lanterns hung around the Milky Way. Their light has traveled across time to reach us, whispering stories of a universe that once pulsed with newborn fire. But even more significantly, the interstellar medium, the vast regions of gas and dust that exist between stars, was changing. As each new star lived and died, the space between them became a swirling mix of ever richer elements. Over time, these chemical legacies would be inherited by each new generation, like cosmic DNA passed forward through stellar ancestry. This cycle of death and rebirth formed a galactic memory. Each enriched star carried within it the story of stars that came before, and in turn, it would write its own chapter through the elements it returned to the universe. The more this process repeated, the more complex the chemical recipe of the cosmos became. Within these enriched clouds, something else remarkable began to form: planets. Unlike the early universe, now filled with metals and minerals, the material necessary for planetary formation was available. Disks of gas and dust circled new stars, condensing into rock and ice, into worlds. Some of these planets would remain barren, locked in endless silence, but some would go on to host oceans, atmospheres, and eventually, life. The second-generation stars planted the seeds of planetary systems. Their enriched surroundings gave rise to new chemical pathways, opening doors to possibilities the early universe could never have imagined. Among these systems, far in the future, one would emerge, a modest star with a golden glow, orbited by a pale blue world rich in water and carbon, teeming with potential. This was the quiet genius of the cosmos. Through death, it became creative. Through destruction, it became fertile. And through the recycling of matter, it laid the foundation for everything to come. As you drift now into a deeper calm, think of these stars, generations upon generations, giving back to the universe so that it might build something new. Even in their fading light, they were never lost. Their dust became planets. Their atoms became air, water, and life. And in a far corner of one galaxy, on one of those planets, that story is being remembered, breathed, and dreamed once more.
Chapter 7: Cosmic Cradles, Nebulae, and the Birth of Stars. Among the most breathtaking wonders of the cosmos are nebulae, vast, colorful clouds of gas and dust scattered across the galaxy like strokes of celestial paint. Though they may appear delicate and ethereal when viewed through telescopes, these immense regions are the dynamic birthplaces of stars. Within their veils of stardust and gas, new suns ignite and take their place in the vast stellar tapestry. Nebulae are the direct descendants of dead stars. When massive stars explode as supernovae, or when aging stars shed their outer layers, they release enormous amounts of material into space. This material, a mix of hydrogen, helium, and heavier elements forged in stellar cores, gathers into clouds that drift across the galaxy. Over millions of years, gravity works its quiet magic, gently pulling these particles together into denser regions within the nebula. These regions, known as molecular clouds or stellar nurseries, are where the next generation of stars is born. Deep within their dark and cold interiors, the density of gas and dust becomes high enough to collapse under its own gravity. As the material compresses, it heats up, forming a protostar, a young forming star not yet hot enough for fusion. But nature is patient. Over time, as the protostar continues to contract and its core temperature rises, a tipping point is reached. Nuclear fusion ignites. Hydrogen begins to fuse into helium, releasing light and energy. A new star is born, and with it, the process begins anew. Surrounding these young stars are often protoplanetary disks, flattened rings of dust and gas left over from the star's formation. Within these disks, particles collide and stick together, growing into pebbles, rocks, and eventually planetesimals, the seeds of future planets. And so, the very same stardust that once formed stars is now assembling into worlds. The Orion Nebula is one of the most famous of these stellar nurseries. Located about 1,300 light-years from Earth, it is home to hundreds of forming stars and swirling clouds of gas illuminated by their glow. Through its beauty, we catch a glimpse of what our own solar system may have looked like in its earliest days. Just another star forming in the shelter of a nebula, surrounded by a growing disk of matter destined to become planets, moons, and eventually life. Nebulae are not only cosmic incubators, they are time capsules. Within them lies a mixture of ancient and new, stardust from long-dead stars, newly forming suns, and the raw material for the future. Each nebula tells a layered story of death and rebirth, of transformation and continuity. When we gaze at them, we are witnessing the creative engine of the universe at work. Even the colors we see in images of nebulae are echoes of the elements within. Reds from glowing hydrogen, greens from oxygen, blues from helium. These are the fingerprints of chemistry on a galactic scale. They are not just beautiful hues, but clues to the ingredients of stars and planets. And from these ingredients, life eventually emerges. When we consider our origins, it's tempting to look only backward, to think of Earth, of oceans and cells and evolution. But our true beginning lies even further back, hidden in the hush of a nebula, in the soft gravitational embrace of dust and gas, in the silent collapse that sparked the sun into being. The nebulae of the cosmos are our ancient wombs. They are places of warmth in a cold universe where dust finds purpose and atoms find light. They are proof that even the quietest corners of space can give rise to brilliance, that even darkness can nurture something radiant. As we move forward, we follow the path of this stardust beyond the stars, to the worlds it helped shape, and to the molecules it seeded across the cosmos. The next step in our journey will take us from stellar nurseries to planetary systems, from the cradles of stars to the solid ground where life begins to stir. But for now, let us rest in the calm beauty of the nebula, a place where silence holds creation, and dust prepares for its next extraordinary transformation.
Chapter 8. Cosmic Chemistry. Stardust meets water. It is one thing to have the building blocks of life, carbon, oxygen, nitrogen, and other vital elements, but another entirely for those ingredients to arrange themselves into something as complex, dynamic, and fragile as life. At the heart of this transition lies a simple yet profound substance: water. Water is more than a liquid. It is a medium of possibility. It dissolves, it transports, it shelters, and it bonds. And stardust, for all its ancient wisdom, needed this unassuming molecule to begin its journey from lifeless matter to living systems. In this chapter, we explore the cosmic chemistry that unfolded when stardust met water, and how this union may have sparked the first steps toward biology. In the early solar system, after the sun had formed and the planets were coalescing, icy bodies swarmed the outer regions.
comets and water-rich asteroids carried not only frozen H2O, but also organic compounds formed in the cold darkness of interstellar space. These icy travelers, remnants from the birth of the solar system, eventually collided with the rocky inner planets, including Earth. These impacts were violent, chaotic, and seemingly random, but they were also acts of cosmic generosity. Each collision delivered not only water, but also amino acids, carbon chains, and other precursors to life. The Earth, once a dry, molten sphere, began to cool. Oceans formed, clouds gathered, rain fell, and somewhere in those newly formed seas, chemistry began to stir. Stardust, now dissolved and dispersed in vast pools of water, found itself in a new environment, an environment capable of shaping molecules, of forming chains, of creating complexity. And though we do not know exactly how, somewhere in this watery cradle, the spark of life took hold. Scientists have recreated some of these early conditions in laboratories, mixing simple compounds in watery environments, exposing them to electrical charges or ultraviolet light, and watching as amino acids and sugars begin to form. These experiments offer tantalizing glimpses into the deep past, into the moment when chemistry became biology. But even before life emerged, stardust and water were already shaping the future. They were building clay minerals that would later host chemical reactions. They were forming ice mantles on dust grains in deep space. They were swirling together in nebulae to birth new stars and planets. The story was not just unfolding on Earth, but across the galaxy, perhaps in countless other places. This chapter of the cosmic tale is one of patience and persistence. Water did not create life overnight. It sculpted the environment, moderated the climate, and created the spaces where stardust could dream of becoming something more. And as you lie still, listening, you are a reflection of that ancient alchemy. Your blood, mostly water, carries salts and minerals that once floated in ancient seas. Your cells rely on the same molecular interactions that may have first occurred in primordial pools. You are, in a very real sense, a vessel where stardust and water still whisper to one another. So let this moment remind you, life is not a miracle of isolation, but a result of cosmic partnerships. The stars gave us their ashes, water gave it motion and memory, and together they shaped a path toward awareness.
Chapter 9: The Architecture of Organic Molecules in Space. In the vastness of the cosmos, amid the chill of interstellar space and the radiation of distant stars, chemistry thrives. While we often associate organic molecules with life on Earth, their origins trace far beyond our atmosphere, beyond even our solar system. They are not unique to our world. In fact, the ingredients for life seem to be scattered throughout the galaxy, waiting patiently in clouds of gas and dust, clinging to icy comets, and drifting silently between the stars. This chapter explores one of the most profound revelations of modern science, that the basic building blocks of life are not just earthly phenomena, but truly cosmic in nature. It began with a mystery. Astronomers, using radio telescopes, detected strange signals, microwave emissions that didn't match any known atoms. As research continued in the 1960s and 70s, these signals were identified as coming from molecules, some surprisingly complex. Formaldehyde, hydrogen cyanide, even simple sugars like glycoaldehyde, each discovered floating in interstellar clouds, some tens of light years away. Their presence suggested that space was not just an empty void, but a chemically rich environment, alive with potential.
But how do such molecules form in space, in conditions so extreme? Temperatures near absolute zero, intense ultraviolet radiation, and immense cosmic rays would seem to destroy rather than create. And yet, within the cold darkness of molecular clouds, complex chemistry unfolds. The process begins with dust, tiny grains of silicates and carbon coated in layers of frozen water, methane, and ammonia. These ices act as tiny laboratories. When exposed to radiation, the atoms within them rearrange, forming new molecular bonds. Over thousands or millions of years, these bonds become increasingly intricate, leading to the formation of amino acids, alcohols, and hydrocarbons. These molecules are then liberated from the dust by the heat of nearby stars or the shock waves of stellar births and deaths, spreading them through space. Some of these molecules are known as polycyclic aromatic hydrocarbons, or PAHs. These ring-shaped structures of carbon and hydrogen are ubiquitous in the universe. They are found in the tails of comets, the atmospheres of planets, and the outer edges of galaxies. Remarkably, PAHs resemble the same kinds of molecules produced by burning organic material on Earth. Their cosmic abundance hints at a deep chemical connection across the universe, one that blurs the line between biology and astronomy. Meteorites, too, have played a crucial role in this story. When fragments of asteroids fall to Earth, they sometimes carry with them a treasure trove of organic molecules. The Murchison meteorite, which fell in Australia in 1969, was found to contain over 70 different amino acids, many of which are not used by life on Earth, but nonetheless demonstrate nature's capacity for molecular diversity. These discoveries suggest that the early Earth may have been seeded with ingredients essential for life, delivered by the steady bombardment of space rocks. Even more extraordinary is the detection of prebiotic molecules in protoplanetary disks, the swirling rings of dust and gas that surround young stars. ALMA, the Atacama Large Millimeter Submillimeter Array, has observed molecules like methyl isocyanate, a potential precursor to peptides, around a young star called Iris 16293-2222. These disks are where planets form, and if they are rich in the ingredients for life, it implies that many newborn worlds may begin their journey already preloaded with life's molecular toolkit. This architecture of organic molecules scattered across the galaxy supports a provocative idea that life, or at least its potential, is not a cosmic rarity. The same chemical seeds that once floated in the interstellar clouds that formed our Sun and Earth might be present in other star systems too. And if that's true, the story of life could be unfolding on countless planets, each shaped by the dust of ancient stars. The cosmos, it seems, is not indifferent to biology. Instead, it may be inherently predisposed toward it. The same physics that governs stellar fusion and the dance of galaxies also gives rise to the chemistry of life. There is elegance in this symmetry, a reminder that we, as living beings, are not separate from the universe, but direct participants in its long, slow transformation. As we continue our journey through stardust, we'll next explore how these organic molecules may have traveled through time and space to find a home on the early Earth. What forces guided them? What environments protected them? And how did lifeless molecules become the architects of living cells? In the quiet of the night, as stars shimmer above, it's humbling to know that the chemistry of life is written in the heavens.
Chapter 10. Stardust and the Chemistry of Life. The connection between stars and life is not just poetic, it's molecular. At its core, life is chemistry, and chemistry is shaped by the availability of elements. The atoms that form our proteins, DNA, carbohydrates and lipids, carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, are not random.
They are the very products of nuclear fusion in stars and the explosive processes that ended their lives. To understand the chemistry of life, we must first understand the legacy of stardust. In the hearts of massive stars, fusion progresses through increasingly heavy elements until iron is formed. Iron is the end of the road for fusion because it doesn't yield energy when fused. When enough iron accumulates, the star collapses and explodes as a supernova. These violent outbursts do more than scatter stardust. They enrich the surrounding space with the full spectrum of life-giving elements. It is these raw materials that become incorporated into future generations of stars and planets. Carbon is the backbone of all known life. Its versatility in forming 4 bonds allows for complex molecular structures. In space, carbon exists in forms ranging from simple molecules like carbon monoxide to complex organic compounds found in interstellar dust. These organic molecules, including polycyclic aromatic hydrocarbons, are among the most widespread carbon-containing molecules in the cosmos. Their presence in meteorites and comets hints that the chemistry of life began long before Earth formed. Hydrogen and oxygen, combined as water, are vital to life as we know it. Water is not just a solvent, it is a participant in chemical reactions essential to biology. Ice has been found in comets, on moons, and in deep craters of planets, preserving the water forged in earlier cosmic epochs. The fact that hydrogen is the most abundant element in the universe ensures its presence everywhere. Oxygen, formed in the final life stages of stars, pairs with hydrogen to spread this life-giving compound across galaxies. Nitrogen, a crucial component of amino acids and nucleic acids, is less reactive, but no less vital. It is also forged in stars and released into space by both supernovae and the winds of aging stars. Sulfur and phosphorus, too, though less abundant, are essential for metabolic reactions and the energy storage molecules of life, such as ATP. These, too, are products of stellar nucleosynthesis. The periodic table of elements is not just a chart of chemical curiosities, it is a map of stellar legacy. Every row and column speaks to a different stellar process, from the slow burn of hydrogen in small stars to the titanic explosions that create the heaviest elements. Without these processes, life's chemistry would be impossible. On Earth, the early environment teemed with inorganic compounds delivered by cometary impacts and volcanic activity, but it was the rich mix of organic molecules, perhaps originating in space, that gave rise to the first protocells. Experiments like the Miller-Urey experiment showed that under the right conditions, simple organic molecules can spontaneously form from a primordial soup. Yet the ingredients for that soup were, quite literally, born in the stars. RNA and DNA, the carriers of genetic information, are constructed from nucleotides composed of sugar, phosphate groups, and nitrogenous bases, all of which depend on stardust elements. Proteins, the molecular machines of life, are built from amino acids that also rely on these same elements. The uniformity of life's chemical language, DNA, RNA, proteins, across all known organisms further underscores the cosmic commonality of its ingredients. Even today, remnants of ancient stars can be found in the solar system. Tiny grains of pre-solar dust have been discovered in meteorites, their isotopic signatures revealing their origins in supernovae and red giants. These grains are older than the sun itself, time capsules from an earlier cosmic era. Their survival through the formation of the solar system and their arrival on Earth is a testament to the interconnectedness of cosmic and biological evolution. The chemistry of life is not confined to Earth. Molecules considered precursors to life have been found on Titan, Enceladus, and in the atmospheres of exoplanets. The fact that complex chemistry is widespread in the universe raises a profound possibility that life is not unique, but inevitable wherever the right ingredients and conditions exist. This view transforms our understanding of biology. Life is no longer a miracle confined to one planet, but an expression of the universe's chemical potential. It is the stardust, not just of matter, but of complexity, pattern, and purpose. As we look deeper into space, we are also looking into our past, not only to the origins of stars, but to the blueprint of life itself. Our bodies are mosaics of ancient atoms, arranged into forms that think, feel, and ask questions about their origin. That stardust, scattered billions of years ago, has come full circle, in the form of beings who now contemplate the cosmos. In this sense, the chemistry of life is the universe awakening to itself.
Chapter 11. Cradles of Life. How Stars Nurture Habitable Worlds. The universe, in all its boundless beauty, is a vast nursery. It creates, destroys, and creates again. In this infinite cycle, stars are not just luminous beacons lighting up the void. They are alchemists and caretakers, sculpting the environments in which life, as we understand it, might emerge. Their light and heat, their birth and their death, their very presence and proximity are all fundamental to the conditions that make a world habitable. To understand how stars nurture life, we must begin with their role in planetary formation. Around newborn stars, disks of gas and dust swirl, coalescing over millions of years into planets, moons, asteroids, and comets. These protoplanetary disks, illuminated and heated by their central stars, undergo complex chemical transformations. Within them, water ice, organic molecules, and silicate grains form and collide, clumping together under gravity's steady hand. As the disk evolves, the planets it harbors settle into orbits, and the star stabilizes, entering the long, steady phase known as the main sequence. During this period, a star like our Sun shines consistently for billions of years, fusing hydrogen into helium in its core. This stability is crucial. Life, particularly complex life, requires time. It needs a stable environment in which temperatures don't fluctuate wildly, where liquid water can persist, and where chemical reactions have the freedom to evolve into biological processes. The concept of a habitable zone, the Goldilocks zone, is rooted in this idea. It is the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Too close to the star, and water evaporates. Too far, and it freezes. The position and breadth of this zone depend on the star's luminosity and size. Massive stars burn brightly but live fast, offering only brief windows of opportunity. Smaller, cooler stars, like red dwarfs, live trillions of years, potentially offering ample time for life to take root, though often with greater exposure to flares and radiation. But a habitable zone is not just about distance, it is also about the behavior of the star. A gentle, stable star provides the nurturing light that powers photosynthesis, drives weather patterns, and warms planetary oceans. Its ultraviolet radiation helps trigger complex chemistry, but too much of it can strip atmospheres and sterilize surfaces. In this delicate balance, stars walk a tightrope. Too calm, and they don't energize life's potential. Too violent, and they obliterate it. Our own star, the Sun, has walked this line well. Its relative stability over the past 4.5 billion years has allowed Earth's climate to remain within life-supporting bounds. The early Sun may have been fainter, but the greenhouse gases in Earth's atmosphere compensated, maintaining warmth. As the Sun brightened over time, Earth's systems adapted.
Oceans circulated, weathered rocks drew down carbon dioxide, and life itself began to regulate the climate. Stars also influence habitability through magnetic activity and solar winds. A planet's magnetic field, like Earth's, is essential in shielding life from these charged particles. In systems with active young stars, this protection becomes even more critical. Without it, atmospheres may be eroded and the surface bathed in harmful radiation. Beyond radiation and warmth, stars help shape life by influencing planetary geology and chemistry. Their gravitational tugs can instigate orbital resonances that stir a planet's core, promoting volcanic activity and plate tectonics, key processes in recycling nutrients and stabilizing climate. Their ultraviolet light can break down molecules and atmospheres, leading to the formation of protective ozone layers or photochemical hazes that act as planetary sunscreens. Stars also seed their surroundings with the essential ingredients for life. We've seen how the deaths of stars scatter heavy elements across space, but during their lives, too, stars contribute. Solar flares and stellar winds can carry charged particles that irradiate ices and dust, fostering the synthesis of complex organic compounds. Around some young stars, astronomers have detected molecules like methanol, formaldehyde, and even precursors to amino acids drifting in the gas between forming planets. The nurturing influence of stars doesn't stop at their own systems. Their light travels across space, reflecting off distant moons, energizing comet surfaces, and stirring the atmospheres of worlds beyond their own. In the broader cosmic context, stars link planets to galaxies, and galaxies to the larger web of the universe's structure. They are both local life givers and cosmic connectors. And what happens when stars die? Even then, they continue to shape the path of habitability. Supernovae can sterilize nearby systems, yes, but they also inject new elements into interstellar clouds, making the next generation of stars and planets richer in life's building blocks. White dwarfs, the remnants of sun-like stars, may host stable planets with enough heat for habitability under very specific conditions. Neutron stars and black holes may seem hostile, yet even around them, hypothetical exotic forms of life, unlike anything we know, could, in theory, exist. From birth to death, from the soft glow of starlight on alien oceans to the furious radiation of a nova, stars are the architects of habitability. They provide more than energy. They offer stability, raw materials, and chemical diversity. They guide the rhythms of climates, the chemistry of atmospheres, and the pulse of evolution itself. And in this gentle night, life finds a way. Whether on a rocky planet warmed by a distant sun, or in the dark seas beneath the ice of a moon reflecting starlight from afar, the cradle of life is never too far from the arms of a star.
Chapter 12. Dust in the Cradle, the role of stellar debris in planet formation. The process of planet formation is one of the most elegant transformations in the universe, a cosmic metamorphosis driven by gravity, time, and the tiniest of particles. It begins with something deceptively simple: stardust. The remnants of ancient stars, once cast adrift in interstellar space, become the foundation for something much grander. From this dust, rich in heavy elements like carbon, oxygen, iron, and silicon, new worlds are born. These tiny grains of stellar debris drift through the galaxy, slowly gathering in dense regions of molecular clouds. These clouds, dark and cold, are the birthplaces of stars and, inevitably, their planetary systems. Within them, dust begins to clump together, sticking through electrostatic forces, forming larger and larger aggregates. Over millions of years, these clusters become the seeds of planets, known as planetesimals.
As a new star ignites in the center of the collapsing cloud, it sends out powerful stellar winds and radiation. These forces sculpt the surrounding disk of gas and dust, known as the protoplanetary disk. Within this swirling structure, the journey of planet formation unfolds. Dust grains pulled by gravity and orbital motion begin to collide and stick together. Some shatter, others fuse. Slowly, chaos gives way to order. The formation of planets is a delicate dance. Too much turbulence in the disk and particles won't stick. Too little motion and they'll simply settle, inert. But in just the right conditions, where gravity and cohesion conspire, planetesimals form. These are the cosmic embryos of planets, ranging from a few kilometers to hundreds in diameter. They collide, merge, and grow, evolving into protoplanets and eventually full-fledged worlds. Stardust doesn't just provide the mass of these planets, it dictates their chemistry. Earth, for instance, owes its metallic core and silicate mantle to the precise composition of dust grains inherited from long-dead stars. The iron in our blood and the calcium in our bones were forged in supernovae and spread across space to gather here, beneath our feet. What's especially wonderful is the role dust plays in the atmospheres of planets. When Earth formed, volatile compounds, water, carbon dioxide, methane, were delivered by dust and ice-coated grains. These elements formed the basis for the planet's oceans and air. Without them, Earth might have remained a barren rock. The presence of water on other planets and moons, like Mars or Europa, is also traced back to this primordial dust. Even gas giants like Jupiter and Saturn, though mostly composed of hydrogen and helium, began their formation from rocky and icy cores made from collected dust. Without that first phase of grain aggregation, even the largest planets wouldn't exist. Stardust is also a key player in the creation of moons. The giant impact theory suggests that Earth's moon formed from debris launched into orbit by a colossal collision. The resulting dust and fragments coalesced into our lunar companion. Around other planets, similar processes created moons from rings of dust and gas. In other solar systems, we've observed these stages in real time. Telescopes like ALMA, the Atacama millimeter/submillimeter array, have captured images of protoplanetary disks around young stars, revealing gaps carved by forming planets. These voids are silent testimony to the invisible hands of gravity and dust at work. And beyond the physical formation of worlds, dust plays a hidden role in their climates and surfaces. Dust storms on Mars, for instance, influence its temperature and atmosphere. On Earth, volcanic dust can cool the planet, while space dust contributes to meteor showers that light up our skies. Even today, the dust from ancient stars continues to shape the fate of planets billions of years after it was first born. It is astonishing to realize that every pebble, every mountain, every droplet of water, every grain of sand owes its existence to the process of dust coalescing in orbit around young stars. What once floated as lonely debris now hosts life, continents, and civilizations. From dust, planets emerge, not merely as rocks or gas spheres, but as the potential cradles of life. The atoms of dead stars find new homes in planetary bodies where chemistry evolves and environments flourish. With time, these once isolated grains become continents, oceans, and eventually beings that look up at the stars and wonder where it all began. And as we gaze into the night sky, we witness the echoes of this cosmic alchemy. Each new exoplanet discovered is a reminder that somewhere in the darkness, dust is gathering again. The cycle repeats endlessly. Stardust becomes structure, and the universe builds itself anew, from dead stars to newborn planets to the seeds of life.
Chapter 13. Stardust in our bones, the elements of life. The stars that once blazed across the skies of the early universe have long since perished, but in their deaths, they scattered across the cosmos the most precious of gifts, elements forged in nuclear fire. Over billions of years, those ashes of creation were swept into new formations, and from them emerged something astonishing, the very bones of living beings. Calcium, the element that gives our skeletons their strength and structure, has an origin story written in the heart of ancient stars. In massive stellar cores, when hydrogen and helium are spent, heavier elements like carbon, oxygen, and calcium begin to form under immense pressure and heat. As these stars explode in supernova, calcium is hurled into the void, destined to one day become part of a living frame. It's a breathtaking notion. Every bone in your body carries within it the heritage of cosmic cataclysms. But it's not only bones that bear this interstellar fingerprint. Teeth, too, made of enamel and dentin, are rich in calcium phosphate, a compound made possible by the generosity of dead stars. Every smile, every bite is an echo of stardust. And yet it doesn't stop there. Phosphorus, essential for DNA, energy metabolism, and cell signaling, was likely formed in a similar way, through the death throes of massive stars and the alchemy of cosmic collisions. Even magnesium, which resides in your muscles and helps regulate hundreds of biochemical reactions, was once part of stellar cores burning at temperatures our sun will never reach. What's truly humbling is how these elements didn't remain floating aimlessly in space. Over millions of years, they coalesced in molecular clouds, bound by gravity, and seeded new planetary systems. Earth, our home, was one such outcome, a world rich in the remnants of dead stars. When Earth formed, these elements became the foundation for geological processes, and later for life. The calcium that had journeyed through light years of space found its way into early organisms, beginning with microscopic marine life that formed shells and exoskeletons. Over time, evolution sculpted complexity from simplicity, and those star-born elements were folded into the blueprints of vertebrates. Fish, amphibians, reptiles, mammals, all carried these mineral gifts in their bones. And humans, we are the latest inheritors of this cosmic lineage. Our bones are more than structural supports. They're historical records. Each femur, each rib, each vertebra is a monument to the stars that once lived, exploded, and gave everything they had to the universe. Every step we take is made possible by the ancient remains of stellar cores. Consider the metaphor, bones as memory. They do not think, do not speak, and yet they hold the entire weight of our past. They hold us upright against gravity, yes, but they also anchor us to the cosmic story from which we came. When you touch your wrist or feel the weight of your body, you are quite literally handling the cooled, organized ashes of supernovae. Modern science continues to explore this connection with increasing clarity. By analyzing isotopes in fossils and rocks, researchers trace the flow of these cosmic elements through geological time. We now understand, for example, how a particular ratio of strontium in teeth can reveal migration patterns of early humans, because strontium, too, is a child of the stars. But perhaps more profound than the science of it all is the poetry of it. The fact that the calcium in our bones was once part of stars dying in brilliant explosions millions or billions of years ago is more than fascinating. It's grounding. It reminds us that we are not separate from the cosmos. We are the cosmos. Our physical being is a temporary arrangement of cosmic dust, Bones may decay, teeth may crumble, but the atoms remain. They return to the earth, and perhaps one day to the stars again. The cycle continues, elegant and unbroken. So the next time you take a deep breath and feel your ribs expand, remember that you are supported by ancient remnants of the stars. You are, in every literal and poetic sense, a structure built from the ruins of supernovae. And in your bones, the universe remembers its past and dreams of its future.
Chapter 14: Birth of Life in the Primordial Soup. In the quiet aftermath of countless stellar deaths and the aggregation of cosmic dust into planetary forms, something truly astonishing began to take shape. On Earth, a seemingly unremarkable blue planet in a vast cosmic ocean, the stage was set for the most mysterious transformation in the known universe, the emergence of life. And at the heart of this miracle lay the legacy of ancient stars. The early Earth, around 4.5 billion years ago, was anything but calm. Bombarded by meteors, riddled with volcanic activity, and drenched in the fierce radiation of a young sun, it was an environment that many might consider utterly inhospitable. Yet within this volatile crucible, the elemental building blocks carried by stardust found a way to interact in increasingly complex patterns. The same carbon, nitrogen, oxygen, phosphorus, sulfur, and hydrogen forged in ancient supernovae were present, swirling through oceans and clouds, absorbed into minerals and drifting in the early atmosphere. Scientists call it the primordial soup, a dynamic, churning mix of water, gases, and organic molecules where life may have begun. Lightning strikes, ultraviolet radiation, and volcanic heat served as sources of energy, triggering chemical reactions among the compounds delivered by meteorites and birthed on Earth itself. These reactions, slowly but steadily, gave rise to simple organic molecules, amino acids, nucleotides, lipids, the essential ingredients of proteins, DNA, and cellular membranes. But how did these basic ingredients become alive? In one of the great puzzles in science is how non-living matter gave rise to living systems. And yet, if we follow the trail of stardust, we begin to see a story of continuity. Life is not a sudden break from the material universe. It is an extension of cosmic chemistry, a new level of organization made possible by the universe's tendency to build complexity. In the primordial oceans, tiny molecules began to form chains, folding and bending in precise ways. Some of these chains, like RNA, could store information and even catalyze their own replication. These self-replicating systems may have been the ancestors of all known life, nestled in bubbles of lipids that protected them from the chaotic outside world. These protocells, precursors to living cells, and they too were composed of atoms forged in stars. It's awe-inspiring to realize that every function of a modern cell, its ability to divide, to create proteins, to process energy, is made possible by the very same atomic elements that once burned in stellar cores. Enzymes that drive biochemical reactions rely on metal ions. DNA strands coil in elegant double helices made of carbon backbones and nitrogenous bases. Even the water that flows through our veins has an ancient origin, possibly delivered by comets and asteroids billions of years ago. From this primordial mixture, over millions of years, life diversified. The simplest single-celled organisms dominated Earth's early oceans, forming colonies, exchanging genetic material, and slowly evolving new features.
Cyanobacteria, for instance, began producing oxygen through photosynthesis, transforming Earth's atmosphere and setting the stage for multicellular life. All of this, every turning point in biology, was powered by atoms born in stars long gone. And yet, while life is made of stardust, it is more than the sum of its parts. It possesses organization, resilience, and the capacity to evolve. These characteristics emerged not through magic, but through a natural process rooted in the properties of matter itself. The same physical laws that govern the explosion of supernovae also govern the folding of proteins and the replication of DNA. This chapter of the story, the transition from lifeless atoms to sentient beings, is often called the Great Leap. But in truth, it was not a single step, nor was it instantaneous. It was a dance of molecules across epochs, guided by chance, shaped by environment, and sustained by the energy still flowing from the sun. Another ordinary star formed from the ashes of older ones. What we call life is a process, not a thing. It's the constant movement of stardust arranged in astonishingly complex forms. It eats, breathes, thinks, and even wonders about its own origins. And in doing so, it becomes a reflection of the cosmos itself, dynamic, creative, and ever-evolving. Tonight, as you listen, know that the cells in your body contain atoms older than the Earth itself. You are not just part of the universe, you are the continuation of its story. The story of stardust did not end with dead stars or planetary dust. It blossomed into oceans, forests, thoughts, and dreams. And this beginning of life, is just the middle of the tale.
Chapter 15. The Alchemy of Planets, Worlds Built from Ashes. Long after the blazing furnaces of ancient stars have dimmed and their cores collapsed into silence, their remnants begin a quiet but potent transformation. The ashes of these celestial titans, rich in heavy elements forged during their explosive deaths, become the foundational dust of entire worlds. Chapter 15 takes us into this phase of cosmic rebirth, the alchemy of planets, and reveals how the same matter that once danced in the heart of dying stars now shapes rocky terrains, swirling atmospheres, and even the seeds of life itself. Our solar system, like so many others, began as a swirling disk of gas and dust, a protoplanetary nebula birthed from a molecular cloud enriched by countless stellar deaths. This material was not pure hydrogen or helium, the two lightest elements born in the Big Bang. Instead, it was laced with carbon, silicon, iron, oxygen, and a host of heavier atoms. These elements are the true legacy of stars. Every rocky planet owes its existence to this celestial inheritance. In this disk, tiny grains of stardust began to collide and stick, bound by static forces and the subtle pull of gravity. Over millions of years, these grains grew into pebbles, then boulders, and eventually into planetesimals, the building blocks of planets. It is a tale of chaos and collision, of gravity assembling raw debris into entire spheres. But not all planets formed equally. The distance from the newborn star determined their fate. Closer to the sun, only materials with high melting points, like metals and silicates, could survive the heat. These became the inner, rocky planets: Mercury, Venus, Earth, and Mars. Farther out, where temperatures dropped, ices could persist, giving birth to the gas giants and their many moons. Yet whether rocky or gaseous, each world carries the same signature, the fingerprint of ancient stars. Earth, our home, formed from this interstellar rubble.
The iron in its core, the silicon in its crust, and the calcium in your bones, none of it originated here. All of it came from stars. The same is true for every planet, moon, and asteroid. Each one is a canvas upon which stellar dust has been painted, reconfigured by time and motion into diverse planetary bodies. And the process is ongoing. We now observe countless other systems with the James Webb Telescope and its predecessors, watching planetary systems in various stages of formation. Around distant stars, disks of dust glow softly in infrared light. We witness the cosmic alchemy that turns death into birth. Some of these systems are young and violent, with planets still crashing into each other. Others are quieter, perhaps even home to life. This planetary formation is not just a byproduct of star death, it is its fulfillment. Stars live to die, and through that death, they seed the future. What was once stellar core becomes planetary crust. What was once plasma, hotter than comprehension, becomes soil, stone, and atmosphere. Life, as we know it, begins not in the glow of the star, but in the quiet dance of the debris it leaves behind. Remarkably, some stars don't just seed one planetary system. In rich stellar nurseries, a single supernova can enrich dozens of nearby clouds, setting off a cascade of planet-forming events across light years of space. Like ripples in a pond, the death of one massive star echoes across time and distance, changing the fates of countless systems. And while this process feels almost poetic from our vantage point, it is entirely natural. The universe doesn't require intent to create beauty. It works through physics, through chemistry, through gravity and time. It is through these blind forces that stars give birth to planets, and planets, someday, may give rise to beings who look up and wonder. It's also important to note that the diversity of planets owes much to the complexity of stellar ashes. A more massive star, for example, will forge a richer tapestry of elements in its life and death. Systems enriched by such stars may form planets with unique chemistries, some potentially capable of supporting exotic forms of life. This idea fuels our search for exoplanets and biosignatures. We are not merely looking for planets, we are searching for the story of their dust. The Earth's early surface was molten and hostile, constantly bombarded by asteroids. But even in those extreme conditions, it retained the signature of stellar matter. Volcanoes belched out gases that became our atmosphere. Water, possibly delivered by icy comets and enriched asteroids, pooled into oceans. And somewhere within that blend of elements, heat, and energy, life sparked. All of it, every molecule of DNA, every drop of water, every grain of sand, was possible only because stars once died, because they ended, and in ending, they left behind the raw ingredients for new beginnings. That is the paradox of cosmic alchemy. Destruction begets creation. The end of one chapter becomes the start of another. So when we gaze at the planets of our solar system, or peer at distant worlds light years away, we are not just seeing new creations, we are seeing the continuation of a very old story, one written in fire, scattered in dust, and reassembled into stone, wind, and possibly even thought. In the next chapter, we follow this journey further, from the solid foundations of planets to the chemical soup that stirred within them, moving us closer to that mysterious threshold where life begins to breathe.
Chapter 16: The Cosmic Recyclers, Black Holes and the Matter They Feed.
In the grand machinery of the cosmos, black holes are often misunderstood as insatiable destroyers, swallowing everything in their path, leaving behind nothing but void. But this image, while dramatic, is only part of the story. In truth, black holes play a profound role in the recycling of cosmic matter. They are not just endpoints of stellar death, they are engines of galactic evolution, influencing the formation of stars, planets, and even life itself through the subtle redistribution of stardust. Let us begin with the basics. A black hole forms when a massive star exhausts its nuclear fuel and collapses under its own gravity. The core shrinks into an infinitely dense point known as a singularity, surrounded by an event horizon, a boundary beyond which nothing, not even light, can escape. But while the core collapses inward, the outer layers may explode in a supernova, enriching space with heavy elements. This explosion is the first step in the recycling process. Now imagine a black hole sitting at the center of a galaxy, surrounded by a swirling disk of gas, dust, and stellar remnants, an accretion disk. As matter spirals inward, it heats up, emitting intense radiation before vanishing into the black hole. This violent process doesn't just destroy matter, it energizes its surroundings. The radiation and outflows from accretion disks can push against clouds of gas and dust, compressing them and triggering the birth of new stars. Thus, paradoxically, black holes help create stars by reshaping the cosmic landscape. Furthermore, black holes are often found at the cores of galaxies, supermassive entities, millions to billions of times more massive than our Sun. Their gravitational pull influences the motion of stars and the structure of entire galaxies. But more importantly, their interactions with their surroundings distribute energy and material across vast distances, stirring the galactic pot, so to speak. This recycling mechanism becomes even more fascinating when we consider that black holes are not eternal prisons. According to Stephen Hawking's theoretical insights, black holes can slowly evaporate over time through a process called Hawking radiation. Though still unconfirmed by observation, this concept suggests that even the darkest objects in the universe might eventually return their mass back into space, contributing, in the most delicate of whispers, to the great cycle of matter. But let's return to the matter falling into black holes. Not all of it is lost forever. Some of the energy and material is ejected in colossal jets, traveling at near the speed of light. These jets pierce the interstellar medium, injecting not just energy, but also reshaping the surrounding clouds. Observations with modern telescopes reveal that these jets can stretch for thousands of light years, sculpting space, seeding it with enriched elements, and perhaps, in time, laying the groundwork for new planetary systems. It's a strange and poetic reality that the very entities we associate with oblivion are deeply connected to creation. Black holes do not consume indiscriminately. Their gravity is selective, pulling in material that ventures too close, but in doing so, they illuminate their surroundings, send out waves of energy, and disperse matter in all directions. These interactions make black holes cosmic regulators. If a galaxy forms too many stars too quickly, the central black hole may flare up, ejecting energy that halts star formation temporarily. This feedback loop ensures a galaxy grows in balance, neither burning out nor stagnating. It's a delicate dance, a gravitational harmony orchestrated by objects that, ironically, cannot be seen directly. We are also beginning to understand how black holes influence the magnetic fields in galaxies. As matter spins and twists around them, it drags magnetic lines into intense configurations. These magnetic fields, in turn, affect how gas cools and clumps together, subtly shaping where stars can form. The tendrils of a black hole's influence, though invisible, are far-reaching.
In the broader perspective, black holes stand as gatekeepers in the cycle of stardust. They're not just endpoints, but crucial agents in the transformation of matter. The iron in your blood, the calcium in your bones, the gold in a wedding ring, all of it came from stars, but some of it may have passed near black holes, been influenced by their jets, or born in the wake of their gravity. To trace the path of stardust is to trace the interactions of all cosmic forces: gravity, radiation, motion, magnetism, and even time itself. Black holes, the silent orchestrators of many of these forces, offer a glimpse into the complexity and interconnectedness of the universe. They are not mere voids, but participants in a story that spans from the birth of galaxies to the emergence of consciousness. So the next time you hear the term black hole, remember, behind the darkness lies not just destruction, but an essential part of the engine that turns dust into stars, stars into elements, and elements into life. The universe doesn't simply erase, it transforms, reuses, and creates anew. In this cosmic cycle, even the darkest points of space become vital chapters in the story of stardust.
Chapter 17. The Stardust Within. Traces in every breath and cell. Stardust is not merely a poetic notion or a distant concept confined to the cosmos. It is the very foundation of our biological essence. Every breath we take and every heartbeat we feel is tied to particles forged in the cores of ancient stars. In this chapter, we explore the profound presence of stardust within us, not as a metaphor, but as a scientific reality embedded in the fabric of our existence. Let us begin with the atoms in our bodies. Hydrogen, the simplest and most abundant element in the universe, was born during the Big Bang. But the heavier elements, carbon, nitrogen, oxygen, phosphorus, and sulfur, these life-essential atoms were formed through nuclear fusion in the hearts of stars. When massive stars ended their lives in spectacular supernovae, they scattered these elements into space. These atoms eventually found their way into gas clouds, into the planet Earth, and ultimately into you. Carbon, the backbone of organic molecules, forms the basis for all known life. It exists in your DNA, your muscles, your brain. Oxygen, the element you draw with every inhale, was once deep within the fiery heart of a red giant star. Calcium, the mineral in your bones and teeth, was created during the explosive deaths of stars. And iron, circulating through your blood, originated in the supernovae that seeded galaxies with metal-rich debris. To understand human biology, therefore, is to trace a journey through the life cycle of stars. Even the air we breathe is infused with the legacy of stardust. The nitrogen in the atmosphere, essential for the production of amino acids and proteins, also originated in ancient stellar furnaces. When you take a breath, you are interacting with particles that have traveled across space and time. In that one simple act, breathing, you are connecting with a cosmos billions of years in the making. Scientific analyses have revealed the isotopic signatures of stardust in meteorites and even in living tissues. Pre-solar grains, microscopic remnants of dead stars, have been discovered in ancient rocks on Earth. These tiny grains, unchanged for billions of years, are direct evidence of stellar processes. Their presence in our solar system and their incorporation into the materials that built our planet confirm that stardust is more than a poetic image. It is physical, measurable, and real. Consider the idea that every living cell in your body is an archive of cosmic history. Mitochondria, the powerhouses of the cell, rely on oxygen to produce energy.
That oxygen was once part of a stellar atmosphere. The proteins encoded by DNA depend on carbon and nitrogen, which came from dying stars. Your thoughts, memories, and emotions are driven by electrical impulses and chemical reactions involving elements forged in stellar crucibles. Even more astonishing is the realization that the atoms in your body are not just from one star, but from countless stars that lived and died long before Earth existed. Each person is a mosaic of stellar remnants, a unique blend of atoms forged across billions of years and scattered across the galaxy. In this sense, we are not only made of stardust, we are made of galactic history. This perspective reshapes how we think about identity and connection. If every person, plant, and animal shares a cosmic origin, then we are all intricately linked, not just biologically, but cosmologically. We are expressions of the universe's desire to know itself. Fragments of stars come alive to witness the cosmos. This truth brings a quiet kind of humility. The elements that form our bodies were forged in the death of stars, an act of destruction that led to creation. In every cell, in every breath, we carry the memory of those ancient stellar deaths, and in doing so, we carry forward their legacy. In the next chapter, we will examine how this journey of stardust continues, not just in us, but in the ecosystems we depend on and in the ongoing dance of matter through life, death, and rebirth on Earth. The story of stardust is not over. It is still being written in the oceans, forests, and even in the deepest cells of every living organism.
Chapter 18, Earth's Living Tapestry, Stardust in Every Ecosystem. When we gaze at Earth's forests, oceans, deserts, and skies, it's easy to become captivated by the diversity of life and the elegance of nature. Yet, beneath every leaf, beneath every tide and gust of wind, lies a deeper origin, a legacy of ancient stars. The ecosystems that sustain life on our planet are not separate from the cosmos. They are living expressions of it, woven from the same stardust that created stars and planets. Let us begin in the forest, where towering trees rise from the soil, their branches reaching skyward like living monuments to photosynthesis. The carbon that forms their trunks and leaves was once drifting freely in the cosmos. Through the quiet miracle of photosynthesis, plants transform carbon dioxide and sunlight into oxygen and sugar, building life from thin air. That carbon, once fused in the heart of a distant star, is now held within bark, roots, and blossoms. Animals that feed on plants, herbivores, consume this stardust-laced carbon, incorporating it into their own bodies. Predators, in turn, feed on them. And so the elements of life pass from one being to another, again and again, in an endless cosmic relay. Insects, birds, mammals, and fungi, each living creature is a brief custodian of ancient particles that once burned in stars, scattered through supernovae, and settled here on Earth. Venture into the ocean, and the pattern continues. The hydrogen and oxygen in each molecule of water has cosmic origins, as do the salts dissolved within. Phytoplankton, microscopic oceanic plants, drift near the surface, performing photosynthesis like trees on land. They form the base of an immense and intricate wood food web, sustaining creatures from tiny krill to massive whales. Fish absorb calcium from seawater to build their bones, just as we do. Coral reefs, among the most complex ecosystems on Earth, are structured from calcium carbonate, the same element born in stars that builds our skeletons.
Even deep-sea creatures living near hydrothermal vents depend on sulfur and iron, both formed in supernovae and now coursing through volcanic outflows on the ocean floor. Deserts, too, though often perceived as barren, are alive with stardust. The sand beneath your feet contains silicates formed in ancient stellar processes. The oxygen you breathe, the nitrogen in the air, the trace minerals in your skin, all cycle through desert winds, rainfall, and underground aquifers. Life here may be sparse, but it is deeply connected to the same elemental legacy found in lusher realms. The cycles that govern ecosystems, the carbon cycle, nitrogen cycle, water cycle, are themselves elegant systems of transformation. Each atom moves from atmosphere to organism to soil and back again. And behind these cycles lies a cosmic truth. The atoms remain the same, though the forms they take shift endlessly. A nitrogen atom in your brain today might once have fed a fern in the Cretaceous or existed in the core of a dying star. Even the decay of life is part of the cosmic story. When an organism dies, its atoms return to the earth, ready to be taken up by other forms of life. Decomposers, bacteria, fungi, insects, liberate elements from once living matter, turning death into nourishment, decay into renewal. This process mirrors the cosmic cycle itself. Stars die, scatter elements, and give rise to new stars, planets, and eventually, life. On Earth, ecosystems are the grand expression of this cycle in action. They do not exist in isolation. Rainforests breathe in carbon, the oceans regulate heat, the tundra stores methane, and each plays a part in the balance of life. They are not just beautiful, they are functional, ancient, and deeply connected to forces far beyond our world. Even the very act of evolution, the slow shaping of life through natural selection, is guided by these elements. The availability of iron influenced blood chemistry in early animals. The abundance of oxygen changed metabolic pathways. The scarcity or richness of certain elements shaped the anatomy, physiology, and behavior of life across millennia. In this way, the story of Earth's biodiversity is also a story of elemental availability, of stardust distribution across time. As we look deeper, we find ourselves again at the center of a grand loop. The food we eat, the air we breathe, the energy we use, all are products of ancient cosmic processes. And as we live, we alter the world around us. Our breath returns carbon to the air, our movements change landscapes, and our choices impact the ecosystems that cradle us. This realization brings with it both awe and responsibility. To understand that we are made of stars is to recognize that all living systems share this origin. It is a gentle reminder that Earth is not separate from the universe, it is an extension of it, a rare and beautiful fragment of the cosmos where stardust has learned to bloom, to swim, to walk, and to wonder. As we move to our final chapter, we'll explore how this entire cosmic journey, from supernova to cell, from dust to consciousness, finds its most profound expression in us. The universe, through stardust, has become aware of itself.
Chapter 19. The Stardust Within Us. Every breath you take is laced with ancient echoes of stellar death. Every beat of your heart is made possible by atoms forged in the hearts of stars long extinct. The calcium in your bones, the iron in your blood, the carbon forming the very core of your cells, all of it, every element heavier than hydrogen and helium, was once part of a star
And not just any star, but one that lived a spectacular life, burned bright and ended in an explosive demise, spreading its material across the universe like a final gift. The dust of stars became the seed of everything that followed, including us. As the cosmos cooled and galaxies spun into their mature forms, this stardust drifted, floated, and collided. Some of it clumped together under the force of gravity, forming asteroids, planets, and moons. Some of it remained free-floating, a cosmic mist that still dances between stars. On our planet, this ancient dust found fertile ground in Earth's primordial soup, where chemistry and physics performed their age-old rituals. Over millions of years, atoms bound into molecules, molecules into complex structures, and life began. Life as we know it is not a foreign anomaly in a dead universe. It is a consequence of stellar heritage. From microbes to mammals, from forests to human civilizations, all are woven from the remnants of ancient suns. Even our thoughts, our creativity, our dreams, they all rely on the electrical signals traveling through neurons made from atoms that were once part of a long-dead star. The story of stardust doesn't end with us, of course. Every living being that dies returns its matter to the planet, where it can be reused, recycled, transformed. Our bodies decay, atoms break free, and someday, maybe far in the future, those same atoms might form part of a new plant, a new animal, or perhaps even a new star. The cycle never stops. In a way, we are temporary constellations of matter. The atoms that form you were once scattered across light years of space, shaped by cosmic events far beyond your control. Yet somehow, here they are, arranged in the astonishingly specific form that is you, conscious, curious, aware. You are the universe contemplating itself. This realization has the power to both humble and uplift. It reminds us that we are not separate from the cosmos. We are part of it in the most literal sense. When we look up at the night sky, we are not merely observers, we are kin. The stars we see shining are distant relatives, and their light is an echo of the processes that brought us into being. As science advances, we uncover more layers of this cosmic lineage. We now understand how the life cycles of stars create the elements necessary for life, how supernovae scatter them, and how gravity regathers them into new worlds. Each step in this process is a chapter in a grand narrative that begins with the Big Bang and continues into the future, perhaps toward other forms of life yet to emerge on distant planets. Imagine a child born on a world orbiting a different sun, breathing an atmosphere formed from the same kind of dust that built our own planet. Their thoughts might also be shaped by atoms that once burned in stellar cores, now reconfigured into entirely new life. In that way, the story of stardust becomes a universal story, shared across time and space, connecting all beings who ever were and ever will be. You are made of stardust. You are not just in the universe, you are the universe, briefly experiencing itself in a moment of reflection and wonder. And that is perhaps the most poetic truth science has ever revealed. So tonight, as you rest, know this: you are the product of ancient light, of stars that lived and died, and whose final breath became the substance of life. Their story is your story, and though the stars may be silent now, their memory lives on in every cell, every thought, and every beat of your stardust heart.
Conclusion. We are stardust still becoming. As we reach the end of this cosmic journey, we are left with a quiet awe that humbles the soul. From the first whisper of hydrogen atoms in the early universe to the grand symphony of galaxies and the flicker of consciousness in the minds of living beings, the story of stardust is one of connection, of transformation, and of endless becoming. We have followed the trail of particles forged in the hearts of ancient stars, stars that lived, died, and scattered their elemental treasures across space. These remnants, drifting silently through the cosmos, would gather again in new clouds, birthing solar systems and worlds, oceans and skies, creatures and minds. The iron in your blood, the calcium in your bones, the oxygen you breathe, they were all created in cataclysms billions of years ago. In this sense, we are not separate from the universe. We are not mere observers of its beauty or students of its history. We are its continuation. We are the universe made self-aware, capable of wonder, curiosity, and reflection. Throughout this audiobook, we've wandered through time and space, not as detached listeners, but as participants in a tale older than memory. We've watched stars ignite and collapse. We've seen planets form, atmospheres emerge, and life bloom in silent cradles. Every step of the story has led to us, not as its final chapter, but as one more verse in a cosmic poem still being written. And as we gaze into the night sky, it's no longer just darkness punctuated by distant light, it's home. Every star is a reminder of our origins. Every galaxy is a mirror of our potential. We belong to this universe in a way that is both physical and poetic. We are made of it. We are sustained by it. We are destined to return to it. The atoms that form us now will someday rejoin the dance, perhaps as part of a mountain, a river, or a comet, perhaps as dust in another star's nursery. The cycle continues, unbroken, timeless, sacred. So let us carry forward this understanding, not just as a scientific truth, but as a guiding philosophy, that everything is connected, that nothing is truly lost, that from the ashes of stars, life rises again and again. And with that, may you rest tonight with a sense of belonging far greater than the span of your arms. You are not alone in the vastness. You are the vastness, condensed, conscious, alive. You are stardust, still becoming.